Okay. 2 minutes. Extra minute. Okay, I think we can start. Good morning to everyone. This is the second day, the plenary talk. I am Marco Lauricella, and I will share the plenary talk now, and then the third session in the room Leone. Okay, today it's a pleasure to present you Benedikt Dorschner. He is a senior scientist at the Swiss Federal Institute of Technology in Zurich. He focuses his attention in general on complex flows, working in particular by the lattice Boltzmann in the entropic fashion, and his interest ranging from different aspect of the fluid dynamics, in particular also including incompressible turbulence, fluid structure interaction, thermal and compressible high-speed flows. He is also the developer of several codes, and the presentation of today is particles on the demand modeling of high-speed compressible flows. So please.
Thank you very much for a kind introduction. It's an honor to be able to speak to you here today. Sadly, not yet in person, but no, we'll make the best out of it. So as you mentioned, today I want to talk to you a bit about how we can model high-speed compressible flows using particles on demand. This is under the scope of an ERC project led by Ilya. And what I will be showing you today is not just my work, but has been contributed by many PhD students, as listed here, also postdocs. Yeah. So let me start by giving you a bit of an overview. I think we can now all agree that LBM really has developed into a versatile computational method. ranging from turbulent flows, where up at the development of more sophisticated collision operators, we really were able to extend the range of attainable Reynolds numbers that we can look at and really have a predictive tool. The same applies in the multi-phase flow regime. I think there also LBM has really developed into a tool which can be used to not just validate, but also really understand and analyze complex flows. Another area where I'm recently becoming interested is reactive flows, and also there I think we can make a valuable contribution. However, now the talk is about compressible flows, and I think particularly in recent years there's been a lot of developments how we can use LBM also in this regime. And here I want to show you the range of Mach numbers here by this arrow that you can see, and I think so far we have been conquering somehow the far left side. So we can do incompressible turbulence, and there's also scope for using LBM in the transonic regime and also in the supersonic regime, but this is still limited to the mild supersonic regime, so still quite low Mach numbers. And today I wanted to talk to you basically about the full range of Mach numbers. And in particular, there's a lot of interest these days in hypersonic flight. So there we, of course, then need a tool how to accurately predict hypersonic flow. This somewhere starts around Mach 8 and then leads to hypervelocity flow. And there's very interesting applications such as atmospheric re-entry, which ranges about Mach numbers 20, 30, something like that. But even further, if you go in Mach up to 1000 and beyond, you have interesting applications in astrophysics. So there's Astrophysical Jet that you want to predict numerically and understand and analyze it for. But now let's talk about a bit about the problem that we are having in really solving compressible high-speed flows. And this starts by looking at the Boltzmann equation in its continuous form. And here you can see it's continuous in velocity space, and we have our Maxwell-Boltzmann distribution function. We know that if we take and do a Chapman-Ansbach analysis, we can recover the fully compressible Fourier-Navier-Stokes equation as shown here by looking or considering the moments, these 5 moments that I'm showing here. So that is our conservation loss, that's the pressure tensor, heat flux tensor, and the 4th order moment that we need to consider in order to get the fully compressible Navier-Stokes equation. Now that becomes a bit tricky if you look at the discrete setting, right? So this is the lattice Boltzmann equation, can be viewed as a discrete version of the Boltzmann equation. So here we also discretize the velocity space here denoted by Ci, and then of course we also need to construct somehow a discrete version of the equilibrium distribution function. And the requirements to really get to the fully compressible Fourier-Navier-Stokes equation is that we have to recover these 5 moments correctly. And this becomes, of course, a bit tricky if you only have a finite set available. And it becomes clear if you already look at our standard lattices. So here in one dimension is d1q3. So this is a particle's velocity at rest, -1 and +1. And of course, if you go to higher dimensions, you can take the tensor product and you will end up with these lattices. But then, of course, if you take higher order moments, you can see that here, Ci cube is going to be Ci. And this implies that the moments are going to be linearly dependent. Thus, we cannot capture all the moments that we previously said that we need to recover in order to go to high speed flows. And you can somehow quantify this error that you're committing by looking at the deviations from the discrete moments to the continuous Maxwell-Boltzmann counterparts. Here I show some errors where, or specific errors. They of course depend a bit on the choice of the equilibria, but the main structure remains very similar. In particular, you have these errors in the Q moment and in the R moment, or the 4th order moment and the 3rd order moment. If you look now here, you have a term which is linear in the velocity and cubic in the velocity. Then you can say, okay, let's fix a temperature that will kill the linear term. So a fixed reference temperature here at 1/3, this will nullify this term, but you're still left with a term which is cubic in velocity. And similar considerations also apply to the 4th order moment. And thus you can somehow say that these errors will only be negligible if you have vanishing flow velocity due to the cubic term here, and a fixed reference temperature T0. Of course, there have been many developments on how to circumvent this, how to mitigate these errors, how to live with them. And I list here a couple of them. So the first route would be to say, okay, if we need to match higher order moments correctly, let's increase the number of speeds that we are tracking. And this led to the development of multi-speed lattices, as shown here exemplarily in this picture. The other route you can say is like, okay, these multi-speed lattices are bulky, they're hard to deal with. Let's stick with the standard lattices. But look at the errors that we're actually committing and counteract them already in the kinetic equations by introducing some correction terms. Of course, there's also hybrid models where you say, okay, let's solve the energy equation, for example, with a different method. So finite volume, finite difference approaches exist there as well. And of course, then there's particles on demand, which I will present to you in a bit of detail today, which is trying to describe the particle distribution functions with respect to a local reference frame, thereby eliminating these Galilean invariants from the start. But let's look a bit in the higher order lattices and actually what they can do. And the first thing you need, of course, is a tool in order to systematically increase your number of discrete speeds. Most naturally, you would look at higher order Hermite polynomials and really use the roots of these Hermite polynomials for your discretization of the particle's velocity space. Here I pasted a table which reports basically the first couple of orders of Hermite polynomials and the corresponding roots, as shown here. You can see that here the D1Q3 is recovered, and this is actually can be scaled such that we have a space filling uniform lattice. However, if you go to higher order, this will not be the case anymore, and you will have to use some off-lattice propagation schemes. There's, of course, another avenue where you can consider also entropy, and this led to somehow a set of admissible lattices, basically supporting a positive and real reference temperature. And this is now on lattice, and I show you here examples of the first couple of orders of velocity sets that you can have here in one dimension. Of course, something else you need to consider is now how would you construct equilibria for these higher order lattices? And there exists also a couple of possibilities. You can again look at your Hermite polynomial expansion. That's one way. You can directly invert the moment system that you're looking at. That's yet another one. And then finally, you can also say, okay, let's look at a discrete H function and minimize this H function subject to some constraints. And this will also lead to a discrete numerical equilibrium. And I mentioned earlier that we have a closure. And of course, if you have a multi-speed lattices, this closure will also be pushed to higher order as shown here. And of course, this will then also affect the reference temperature that you're dealing with. Now let's look at a bit of the accuracy of these type of schemes. And here I show you the deviations of the heat flux in the fourth order moment with respect to the Maxwell-Boltzmann counterpart. And you can readily see here, this is the error in terms of advection Mach number. And you can see that if you increase the advection Mach number, the error will increase irrespective of the lattice that you're choosing. However, the error will be smaller if you're choosing a higher order velocity set. So the higher you go in the order, the more or the less errors you have if you increase your Mach number. But you can already see that it's quite of a slow increase. In particular, if you look at Mach number 1, so you want supersonic flow, you already need 49 velocity lattice in 2 dimensions. And that is, of course, kind of a slow increase. Now, similar picture arises if you look at the temperature deviations. And here, this is shown at with a theta here. So theta 0 corresponds to the reference temperature. And if you deviate from that, you can see in these 2 plots that the error, you will accumulate errors as well. It gets even worse if you superimpose a local advection Mach number, and then these errors will rise as well. You can also look at now positivity ranges of these equilibria. And here I show a table of the temperature ranges that you can actually achieve with these lattices. And by temperature ranges, I mean, those are the temperatures that you can have where the weights, which are now temperature dependent, are still positive. You can see that in the standard lattice, it actually supports an infinite range of temperatures between 0 and 1. But if you go higher in order, this ratio actually decreases quite rapidly. Thus posing the question if it's really the way forward to really large Mach number flows, because if I increase the velocity set, I will diminish the temperature range that I can actually accommodate in this lattice. However, you can do something. And here I show you simulations from Niccolo Frappoli. He was doing a lot of simulation, and they actually have shown to be very accurate. So if these schemes work, they are very accurate. He was simulating here a transonic airfoil. And he computed also quantities like the pressure coefficient and compared it with DNS. And it was actually quite an accurate match, even for quite under-resolved simulations. He also did supersonic flow simulations, here shown exemplarily with this supersonic double cone. And again, we could compare it with an analytical solution. And you can see that even with quite coarse resolution, you were able to capture everything quite accurately within an error of 1%. So you can do something, but as I mentioned earlier, now we have to see what we can do. So higher order lattices work. They can increase the range of attainable Mach number. It's a slow increase though. And actually the temperature range decreases with an increasing number of velocities. So that somehow questions if this alone is a path towards very large Mach numbers. Now, as I mentioned earlier, you can say, okay, let's ditch higher order lattices and let's stick to standard lattices and then correct the terms that we actually, or the error terms in the hydrodynamic limit, correct them directly in the kinetic equations. And here I show you again the errors that we are committing, just to remind. And now we've been working on that, which is called an extended lattice Boltzmann method. And this is basically aiming to correct these errors. So you can do this by realizing that you can actually correct these errors when you impose different pressure tensor. And this is now not just the equilibrium pressure tensor that we usually have, but also takes into account the derivative of the deviation of the third order moment. And you can impose that by moment inversion is one way, or you can write it, as I show here, more compactly as a product form equilibrium, where it's a product of these triplets here. So that's one part for the third order moment. You also have to look at the fourth order moment and the heat flux itself. And here you can also impose it directly, in the sense that here we look at the moments of the Maxwell-Boltzmann energy distribution functions, use a second population in order to impose that. And here you can realize that you can generate these moments with these operators as shown here. And then if you replace the energy coming from this Maxwell-Boltzmann with a more generic energy, then you can compute your moments, impose them correctly, again, via moment inversion slash the operator product form as shown here. And then actually all the moments that you impose will be recovered correctly. Now, that this actually works. I want to show you very briefly a simulation of Fosse and Sadat, who actually will have a talk later on and discuss this in a bit more detail. And this was the simulation of decaying, compressible, homogeneous isotropic turbulence. So Reynolds number is 175 and turbulent Mach of roughly 0.5. So that's a complex flow because you have turbulence, but you also have local supersonic regions, so-called eddy shocklets, as you can see here, by looking at isosurface of velocity divergence and then colored by local Mach number. And you can see here that it actually goes up to 1.4 locally. So there you again have to capture on one hand, you need an accurate scheme not to kill all the turbulence, but you also need to be stable enough in order to capture the shocks. And he was able to compare now statistics with DNS simulations. So here shown by the dissipation rate, as well as the Reynolds number based on the Taylor microscale with time. And you can see that actually these schemes are quite accurate and can be used to simulate these type of flows. Now, what I've shown you so far, so these schemes are very comfortable in the regime that I've been showing previously. So this is in the range of transonic, mild supersonic flows. I promised you to go a bit further to look at the upper range, for this, I will introduce particles on demand. I will start by reminding again that lattice Boltzmann itself can be considered as describing the particle distribution functions of populations with respect to the laboratory reference frame. That means zero velocity and a fixed reference temperature. So that leads to the fact that the peculiar velocities are going to be your discrete velocities, and you're going to be having a stencil looking like that throughout your domain, fixed and constant. As I've previously shown you, that this will lead to some errors, and you will go into some trouble if you simply increase the Mach number. However, in particles on demand or POND, we say, okay, let's find a way how to describe these populations with respect to the local reference frame. So this is now depending on the local flow velocity and the local temperature. And then you simply have to rescale your populations accordingly and shift it by the local flow velocities. And this, of course, will then lead to lattices, which will be spatially varying, as shown here, depending on local flow conditions. What you will get, however, is full Galilean invariance. That means what this local reference frame actually implies is that the populations only see macroscopic quantities with respect to the local gauge. That means in your equilibrium, for example, will be evaluated at zero velocity and the reference temperature directly, basically leading to just a density dependence times the weights. And now it also implies if you take the moments now here with these scaled and shifted velocities with respect to some reference frame, you will actually recover all the moments that you will actually need in order to recover fully compressible Navier-Stokes. So all the troubles that we had before will vanish once I'm in the local reference frame. Now the question comes, how would you do that? How would you be able to describe these populations in a local reference frame? And for this, we need a tool to map from one reference frame, let's say here at rest, to a local reference frame. And in POND, we say, let's match the moments. And we say all the moments should be equivalent independent of the reference frame I'm choosing. And you can write this out as shown here. You can invert the system and you will end up with a transformation matrix here, G, which will map populations from a reference frame lambda to lambda prime. And this transformation always exists. Now, the kinematic equations, they actually don't differ that much. So you have your collision term shown here. Now, the equilibrium, as I said earlier, becomes trivial. So that's a benefit. On the other hand, the propagation will be a bit more tricky. Tricky, why? Because these discrete velocity speeds will depend on space and time, right? So there we necessarily require an off-lattice propagation scheme. And I introduce here really a generic way how to reconstruct these populations with some interpolation functions. That's not necessarily important right now. And what's important is to note that here we need to transform these populations to the given gauge or reference frame in the monitoring point where I'm trying to reconstruct. Now, what is important to realize is that the characteristics still remain constant. So there's no derivative of sorts of these discrete speeds. That's simply because conceptually you can think of this as transforming the entire computational domain into the reference frame you want, doing your propagation transform back. However, of course, in the discrete setting, you don't have to do that because the advection procedure will only concern a small region around the monitoring point, nearest neighbors or one beyond. So now the question is, how do we get this local reference frame, right? So we know that once we are in the local reference frame, everything is well behaved and works well. The question is how to get there. And we get there by an iterative predictor corrector search. Basically, we initialize the system with previous time step values. We can thus compute our discrete velocities, do an off-lattice propagation of sorts, compute macroscopic fields, because they are now new, because you have distributed your mass, momentum, energy, and so on, which then necessarily leads to a new reference frame. And then you have to check if you have converged, and by converged mean, did the reference frame change? If it has changed, you keep iterating until it converges. And once it converges, you're actually in the local reference frame, and you can carry out your collision and the next time step. Here's a note on the convergence of this whole thing. It's somehow a fast convergence in the sense that typically we don't require much more than one iteration in regions where you have smooth flow, and only at in regions where you have large gradients, discontinuities, there you will have iterations which go beyond one. But still kind of small, they range between 4, 5, 6, something around that. So that this thing actually works and is fully Galilean invariant, I want to show with them basic validations. And here I plot the viscosity and its dependence on the advection Mach number. So physically, of course, this should not affect it, but you can see if you use a normal LBGK model, then you will have the spurious dependence of the viscosity on the Mach number. If you use Pond, on the other hand, this does not happen, even for different temperatures that you're going to be imposing. The same thing appears if you look at the speed of sound. So we know that if you just use a normal LBGK, you will only be correct at a singular point, that is the reference temperature, and everything deviating from that will lead to an error. However, in Pond, you can actually recover a wide range of temperatures. Even if you superimpose an advection Mach number of here 100, it doesn't really matter. It will fully recover your correct speed of sound. More pictorially, you can look at the vortex ring, which is now advected in the flow. And you can see that if you use LBGK, you will have some spurious deformations once you increase the advection Mach number. In Pond, however, it actually remains round and no deformation because you're fully Galilean invariant, and you can even go up to Mach numbers of 100. It doesn't really matter. Previously, I was a bit vague about the choice of the off-lattice propagation scheme. And that was for a reason, because there are many different methods that you can use, and you can more or less generically incorporate Pond in them. So previously, we've been using a semi-Lagrangian advection scheme, which works, but also has some drawbacks, especially if you use Lagrange polynomials or something like that. I encourage you to check out a bit Nikos Kalkounis' talk. He will talk about finite volume schemes, because there's the main benefit that you rigorously conserve mass. And on the DAX side, of course, you can get away with much less velocities. But you can also use finite difference schemes. You can use hybrid schemes, LBM, Pond. You can snap them into the lattice if the flow actually allows that. There's also other approximate versions like regularizations and so on. In terms of the reconstructions themselves, we've been also playing with moment conserving interpolations that we borrowed from the vortex particle community, but also higher order Venus schemes, limiters, and so on. So those really help if you really go to large Mach numbers with a strong discontinuity. And for those schemes, Ehsan will also talk, I think in the next talk, a little bit more in detail on the numerics. Okay, so now one other thing to note is that Pond is quite universal in the sense that we can use all the different models that we have already developed in LBM within Pond. So we can use our two population models, quasi-equilibrium models. You can also use your favorite multi-phase model, multi-speed models for non-equilibrium flows, and even detonation simulations are now possible. And in the following, I want to show you a bit what you can do with those. So I will start with the cases, hard 1D cases, because you will first need to capture really strong discontinuities in 1D. If you can do that, then the extension to 2 and 3D is rather straightforward. So, and the first thing I'm going to show is that of a shock density wave interaction. So you have a shock wave of Mach 3, which will be interacting with a sine wave in density. And we did this with a two-population model using 9 speeds. And we compared this with a higher order Dino finite difference scheme. And you can see that actually Pond is able to recover what the DNS produces. So this is actually a quite sensitive test case because these oscillations are very tricky to capture accurately in terms of phase and magnitude. So here we're quite happy, but this is still kind of a mild shock, right? So that's Mach 3, but let's go a bit further. And here I want to show you the setup of a strong shock tube. And by strong, I mean it is strong in terms of the pressure ratios. So here we have a pressure ratio of 10 to the 5, so 5 orders of magnitude difference. That's far beyond what you typically see, like saw shock tubes and so on. So this is much higher, which leads somehow to an apparent Mach of roughly 200. But of course, it's a nice setup because we have an analytical solution. And this is what I'm showing here is the comparison in terms of pressure and velocity with the exact solution and Pond. You can see actually the dynamics is captured quite well. You have some small oscillations, but this is, of course, somewhat normal and depends also on the reconstruction scheme. And also all the classical solvers will exhibit these type of behavior. Another regime that we looked at was compressible multiphase flows. And here also Pond or the whole ideology behind it is nice because it lets you impose the non-ideal gas pressure directly by scaling the discrete velocity Ci here, and then again shifting. Of course, all the surface tension effects and so on will have to be imposed as usually. Here this was a simulation of Esan, who was also able to compare with experiment by looking at the droplet centerline with evolution. So, and he did this for a few Mach numbers and was actually getting quite a good agreement with the experiments. Then we also looked at non-equilibrium flows. And this was a simulation of Nikos, who was looking at a one-dimensional planar shock wave of Mach 1.6. And of course, we know the continuum Fourier-Navier-Stokes equation will fail. Because you have non-equilibrium effects. And that's why we also here did simulations using a multi-speed lattice. He actually did something more sophisticated in the sense that he used a multi-scale approach where you have different lattices in different regions of the flow depending on the local Knudsen number criterion. But that's not necessarily the point here. The point here is that you can actually capture quite accurately non-equilibrium effects with Pond and the multi-speed lattices. So those are not necessarily counterintuitive, so you can really combine them as well. The last 1D setup that I wanted to show was that of a one-dimensional detonation. This was a simulation carried out by Nilesh. And here we use a very simple phenomenological model. Here solving simply a convection reaction equation and then based on a simplified Lee-Tarver model, as shown here, where you have a threshold temperature, which basically activates your reaction. And then you can add the temperature change due to this reaction as a source term in your energy equation or the population for the energy. And this is also a nice setup in the sense that you can compare with an analytical solution, which exists at these Chapman-Duguay points, where detonation basically propagates at sonic speed with respect to the leading shock wave. And he was doing that for various heats here, basically changing the Mach number. And he was comparing up to Mach number of 7 with the theory. And as you can see, it's actually quite a good match. And the same goes for the temperature. So we can capture these type of flows quite accurately with Pond, even for large Mach numbers, as shown here, up to Mach 7. So this is promising if you now want to go to a more complex systems in 2 dimensions and 3 dimensions and look at detonation there. Last but not least, I promised you the full range, and here I want to show you somehow an astrophysical jet at a very large Mach number. So you have a jet which comes in at Mach number 1000. And this was a simulation still using 9 speeds and 2 populations. It's extreme in the sense that you have an extreme pressure ratio. So the ratio goes up to 5 orders of magnitude difference, or and in both pressure and also temperature. And here in this movie, I show you the evolution of the logarithmic density. I will not go too much in detail there. I think Esan will talk a bit more about what you can actually see here. But this is just to say that Pond also works for extreme Mach number flows. That comes to the end of my talk now. So what I was trying to convey today is that a couple of ways how you can do compressible flows with LBM or kinetic schemes in general. If you look at higher order lattices, correction models, they are very accurate, very efficient, but they're somehow limited in the range they can achieve. So you are somehow on the low Mach number end of the spectrum. And you can use Pond to eliminate these Galilean invariants and actually capture the full range in Mach numbers. And this, of course, opens up very interesting perspectives. We can now look at things like atmospheric reentry problems. Of course, we still have a lot to do in order to capture those accurately, but at least there's a path towards this now. Also interesting applications like the supersonic parachutes that you will find for mass landings, for example. This is something which interests me at the moment, and in particular because we can now use all the knowledge that we already have from the lattice Boltzmann in terms of fluid structure interaction and so on directly into Pond, and yeah, and then basically tackle these type of applications with that. With this, I would like to thank you, and I'm happy to take any questions.
Thank you. Thank you very much for this really interesting presentation. We see if we have a question in the chat. It's a bit long, but I don't know if you can read directly. It's the first. As a general comment, it is very surprising to see that you are not talking about efficiency of the proposed approach, while it is the only things that matter science.
Okay, so I don't necessarily think, so efficiency is obviously a concern typically. I don't think that matters too much. At the first step, we want a solver which can actually go there where we want to go. So I think we want to explore the full range in Mach. And of course, if you still keep the kinetic part of all these things, then you already gain something, right? In terms of non-equilibrium flows, multi-phase flows, and so on and so forth. And of course, you can optimize this as well. I mean, the off-lattice propagation is not necessarily the most efficient one. That is true. But as I mentioned previously, you can combine them with LB itself. You can have somehow a discrete reference frame space, which then mitigates the cost of all these transformations, all these iterations, and so on. So I think there, in terms of optimization, you can do quite a bit, and that's not necessarily of concern here. And I don't think necessarily that DVMs and ducks and so on are orthogonal to the concept of what I'm presenting here. On the contrary, you can actually, incorporate them into Pond and vice versa, which will lead for ducks, for example, to a conservative scheme, but also reduce the number of velocities that ducks would need in general, right? And the same goes for DVM. DVM is.
I'm sorry, I will have to interrupt you. So here you are saying that you could indeed, let's say, write a DVM or UGK formulation of Pond, but this assumes that adaptive lattices have not already been published in the context of DVM and UGKs, but it has already been published.
Well, so as far as I know from the people we're working with at the moment, DVM typically has a problem of actually finding the discrete velocity sets, like the scalings that you typically have, and so. And this is a non-unique thing and actually problem dependent.
I'm not talking about DBM. I'm talking about the VM, discrete velocity models, like those used for rarefied gas flow simulations since the early 2000s.
Yeah,
what you're talking here is the work by Aigo Xu, for example, in China, and this is DBM. This is completely different.
Yeah, sure. Okay.
Okay. There is another question: how to determine the number of lattice in your model, and what is the principle?
The principle is, at the time being, we kind of stick to 9 velocities at the moment, because if that's sufficient,
yeah.
we typically use a dual population approach in order to impose a variable adiabatic coefficient. But again, if you want to go to non-equilibrium flows, this will not be sufficient. You will not be able to resolve the shock fully if you stick to 9 velocities, in particular when you're in a co-moving reference frame and then all the velocities pointing in one direction, you cannot fully resolve the shock. That will require an higher order lattices in the end.
Okay. So thank you a lot for this presentation. We don't have a clap since we are still in this strange world made of COVID and pandemic stuff. But thank you. I can go
Thank you very much.
for you. Okay. So now I want to remind to everyone that the conference from now is split in 2 different sessions. Here we will continue with the third technical session, compressible flows, while in the room Palma now we'll start the 4th technical session about the advanced methods. Okay, so now I invite the next speaker. Okay, I can. Okay. So the next speaker is Ashan Rayhanian. He is from the Department of Mechanical and Process Engineering in Zurich, and the title of the presentation is Particles on Demand for High Mach number flows. Please.
Good morning. Do you see my screen?
Yes.
Okay, perfect. My name is Ehsan, and I'm a PhD candidate at the Computational Kinetics Group of Professor Carlin at the ETH University. And today I will be talking about the particles on demand method with the application of highly compressible and high Mach flows. So as a brief introduction, the lattice Boltzmann method has been successfully applied in different domains of computational fluid dynamics. One can exemplify turbulence, multiphase, and despite the success of lattice Boltzmann in these domains, most of the applications so far to date are still restricted to low Mach number flows. Even if compressible, the range of the Mach numbers are still restricted. And all researchers, people are still trying to come up with a simple yet genuine model for with kinetic roots to simulate high Mach flows. And within the framework of kinetic theory, there have been some methods developed so far, all with some advantages and disadvantages of their own. But as a recent method, recent and novel method, I have chosen the particles on demand method for my research. And today I would like to show some applications of particles on demand on high Mach number flows. So we had a very comprehensive talk on the introduction of Pond, but a very brief introduction on my side. So in the Pond framework, the conventional discrete velocities known as the lattice are rescaled with the local square root of the local temperature of the flow. And this will get rid of the temperature restriction that we have in LBM. And then those velocities are shifted by the local velocity of the flow. And this will give us, bring us the Galilean invariance that we are missing in lattice Boltzmann methods. So usually in lattice Boltzmann methods, one of the methods to use equilibrium is to use the truncated polynomial in velocity, and that is the main reason that these schemes are not Galilean invariant. But here we have an exact equilibrium depending only on the density and the weights, and this will bring us an error-free collision. We also realized that the Pond scheme would reduce to lattice Boltzmann if the temperature is simply chosen as the temperature, as the lattice temperature, and if the global reference frame is set to 0. However, these discrete velocities are no longer integers and space-filling, essentially, so that simple point-to-point streaming that we have in lattice Boltzmann is no longer the case here, and we have to use different methods. For example, I use the semi-Lagrangian advection, which will require interpolation. And the way we do that here is, so if we want to update the information at the monitoring point X, we travel back in time through the characteristics where we reach the departure point, and this departure point is will not be essentially a node point. So some amount of collocation points will be used to interpolate for the desired information. After that, the macroscopic values will be evaluated, and we want to iterate this process until the convergence of reference frames are achieved. And at that point, we are sure that we are at the co-moving reference frame where we can use the exact equilibrium function in the collision. And this is the big picture. Now we want to be going to the little detail here as to how we can do all these reconstructions and how they would affect our simulation. So the reconstruction is simply the interpolation of the transformed particles. We want to transform the populations before using them, before advecting them in order to be consistent. So they must be transformed to the reference frame of the monitoring point that we want to advect these particles to. So after transforming those, we want to interpolate these transformed particles on all these collocation points. And for the interpolation kernel, well, there are different choices in the literature which have been extensively used before. For example, one can use a moment conserving interpolation, where in this scheme, a finite number of moments of the interpolated field, interpolated quantity, is conserved during this interpolation. One can use the simple classic Lagrange polynomials, which actually can overlap with this moment conserving at under some circumstances. And also we have B splines, which are smooth functions, and so on. So there are so many choices. And but so if you want to have a compressible flow simulation, if you want to have a high Mach flow simulation, we will have shocks and discontinuity. This is a very classic problem that if we use these interpolation kernels, and because they have negative weights, they produce negative weights, the solution will become oscillatory, and these oscillations will eventually kill the whole simulation, especially in our scheme that our discrete velocities are the function of square root of temperature. So if these oscillations would lead to a negative pressure on temperature, then it will essentially kill the simulation. So to overcome that, we use two types of remedies. One is the phenotype interpolation, where we choose between the substencils And the other one is to use the total variation diminishing concept, where the total variation of the solution remains finite and not increasing in time. So the Vinode interpolation, well, the Vinode scheme is a very well-known, but just a brief introduction is that the main stencil is broken into different sub-stencils, and where these sub-stencils are assigned, each assigned with a weight. And if a sub-stencil would include a discontinuity, then the weight of that sub-stencil would be negligible. And finally, the convex combination of solutions at each of the sub-stencils will guarantee an oscillationless final solution. This is one way that we can deal with shocks and discontinuities. The other way that we have used is the concept of TBD, and we apply that to an improved, well-known BS spline known as the K3 BS spline. So all BS splines are second-order accurate. So, but we can improve those. We can have third-order accuracy. And as I said before, the BS splines are smooth functions. They have a continuous derivative. So, for example, if we compare this BS spline to the fourth-order Lagrange polynomial, you can see the smoothness of this and the continuous derivative of that in its range. And actually, this brings us a very good mass-conserving property, as we can see in our simulations. So with that in mind, we apply TVD on top of this interpolation kernel to have oscillationless solutions, because as we can see here, we still have values below zero that are negative, which will lead to oscillatory solutions. In the following, I will present some benchmarks, classic benchmarks for compressible flows. And as said before, I will use the Vino and TVD BS spline schemes. And just for the sake of comparison, I will show a result of Lagrange polynomial fourth order, just to show that these polynomials, these simple interpolation kernels, would not be a good choice, a proper choice in compressible flow simulations, as they are oscillatory. The CFL number is a function of the maximum of the value of the discrete velocity in the whole domain. And in all of the benchmarks, the specific heat is set to 1.4 unless stated otherwise. And to have the specific heat, we simply use the double distribution function method. So first, I would like to show the Schwarzer Shock Cube, which is a very mild case in the compressible benchmarks. The CFL is set to 0.4. We have implemented this problem with 25 and 9 velocities. For example, in this 25, we can see that this red line, which is the fourth order Lagrange polynomial, shows oscillations at the location of the shock. Also, so this is the density and this is the velocity field. These oscillations are also very visible in the velocity at the discontinuity and at the shock. Now, this is a very mild case, but these oscillations can actually, so they cannot be tolerated in severe cases, in more extreme cases. And the simulations actually is not possible with these simple kernels. But on the other hand, our TBD and Vino scheme gives us a very clean and nice result where we have no oscillations on the location of the shock and discontinuity. And the same explanation goes for the non-velocities as well, where we see that oscillations have been removed from these plots. So I go a little bit further. I show the Lux Shock Cube problem. The CFL is the same number, 0.4, even though I have compared with lower CFL numbers. So for example, if you use the fourth order Lagrange polynomial, this will not work in these problems. And this is even not a very extreme case. So here again, we see that for 25 and 9 velocities, location of the shock and discontinuity have been captured well. It is a nice agreement with the exact solution. And more importantly is that the oscillations have been successfully removed from the solution. So if we go a little bit further, we have a Mach-3 shock front interacting with the perturbed density field. So here again, with this CFL number and both 9 and 25 velocities, the location of the shock is captured free of oscillations. Also, the shocklets and the post-shock waves are captured, and they are in good agreement with the exact solution. And here we see that with increasing the resolution, we can actually converge to the exact solution. So moving on, this is the last 1D case that I would like to show. So this is the strong shock tube as shown by Benedikt. So this problem is strong in the sense that it features a Mach number of 198. We fix the CFL to 0.1 here. We use 9 velocities, and we see that the TVD scheme has a very good performance in this problems. So this is the density and temperature field, and we see that the temperature ratio is 10 to the 5, which is far from the performance range of, let's say, lattice Boltzmann methods. However, on the other hand, the Vino scheme has a slightly poor performance with respect to the TVD, and I believe that this is because of the mass conservation problem, because as we know, the semi-Lagrangian schemes are in general not mass conservative. And as I said before, these BS splines have a very good mass conserving property, which leads to a very good performance even in these extreme cases. But this Vino scheme, actually, they do not have this property, and that is why they might diverge a little bit in very extreme cases. But overall, the performance of Vino have been quite good, actually. And for the last test case, the Astrophysical Jet, which was shown by Dr. Dorschner. So here the Astrophysical Jet is referred to very high speed gas flows, which are observed by the Hubble telescope. And we do not consider the effect of the radioactive cooling, which is actually the case in reality. So it is conventional to refer to the Mach number with respect to the cold jet, and here the Mach number is 1000. So we fix the CFL to 0.1. We have a different value of gamma here. So we see that the density and the temperature contours here, other than the stable solutions, which is actually very important in these test cases, because we have a huge amount of kinetic energy, which can simply lead to negative values of temperature, which is again a classic problem in high-speed gases. We see that the general features of a supersonic jet, as for example the bow shock, the instabilities of the jet tip are captured. So with that, I would like to wrap my presentation. So in conclusion, the Pond method uses a set of discrete velocities, and with that, we are given with the Galilean invariance, which we need for high-speed simulations. But of course, when we need to augment this method with some shock capturing schemes, so that we would be enabled to simulate high Mach number flows. Well, this is still an ongoing research, and we are looking forward to extend the application of this model in 3D applications. Thank you very much, and I'm open to questions.
Thank you. Thank you. And I don't know if there are questions.
Maybe I have a quick question. So thank you for your presentation.
Please.
Yeah.
So you said that your scheme is TVD, right?
Yeah.
And how can it be TVD if you are not using a Ruggie-Kutta time integration?
So this is a spatial reconstruction.
TVD means that between two time steps, your total variation will not increase.
Yeah.
That means that you also need a proper time integration scheme.
Well, I can, well, not now, but I have actually tracked the total variation of this scheme. And if it was not TVD, then your solution would be oscillatory, right?
No. the non-oscillatory behavior comes from the Weno scheme.
Sorry, from what?
The Weno scheme, W-E-N-O.
Yeah, I know what is Vino, but Vino is not the only way. So you can use TVD schemes. It is in the literature. It's very classic.
Yes, but you need a proper time integration scheme for that.
That is for the time integration. But
no. If you want a TVD scheme, it's both in space and time.
Well,
I mean, this is basic numerics, huh?
Well, yeah, this is basic CFD, and you can have a spatial reconstruction that is TBD. And if that was not TBD, all the simulations were not possible. So when you see no oscillations, the main concept of TBD is to remove the oscillations, so that it would change the order of accuracy.
It's to not have a local extrema that appear. That's the main definition of TVD.
Well, I refer
local
to
extrema or
the
minima.
literature, sir.
I have a question from the chat. Another question. Did you verify mass conservation in the simulations?
Sorry. Yeah. So, for example, when we use this B-spline kernel, we have almost exact conservation of mass, even in very high, in severe cases. It has a very good performance in mass conservation. And that is why we chose this kernel and we applied the TVD on top of it.
This is another interesting question. Can different particles come to the same point?
I'm not sure I understand the question.
Probably it's not in the sense if you can have two different particles that come at the same point. I think this is not possible, if I have understood the method, in the sense that you change the position, no? To match
I'm not sure if they are talking about, for example, the advection step that we get from different points. So because the discrete velocities are not symmetric like in that Spokesman, so we get particles flowing into the monitoring point from different places in space. If that is the question, still not sure that is the right answer.
Okay, I think we can move to the next speaker. Okay, let me invite him. Ecco qua. Okay. Okay, so you can share the screen, I suppose. Okay, we can see. Okay, the next speaker is Kalli Kunis, and the title of the presentation is DAX in point D, a finite volume implementation of the particles on the method. Please.
So, good morning. My name is Nikos Kallikounis, and I am a PhD student of Professor Karlin Group. My talk today will be about DAX in pond, or in other words, a finite volume implementation of the particles on demand method. The lattice Boltzmann method is an accurate and reliable CFD solver. The simple streaming step along the lattice links and the local collision step make LBM a very efficient method, competing commercial and other well-established CFD methods. However, at the same time, the lattice puts severe constraints into the attainable flow velocities and temperature ranges. To remedy these constraints, the particles on demand method, or pond in short, allows the particles' velocities to be guided by the physics of the flow. Experience with pond has shown that the operating windows of the kinetic models can be extended considerably, and high Mach compressible flows with large temperature ratios are now possible. As we already saw, most of the previous works with pond were designed with a semi-Lagrangian numerical scheme. And although this method is simple and offers several advantages, the main drawback is that it does not allow easily the mass and momentum and energy conservation. And in this work, we wish to address this problem by exploring a finite volume discretization scheme. With this viewpoint, our domain now consists of a set of control volumes and cell phases. The key element in this method is the calculation of the fluxes which passes through the cell phases. And since the flux that enters a given cell is identical to that leaving the adjacent volume, these methods are in general conservative. So in this work, we will follow the finite volume implementation of the discrete unified gas kinetic scheme, or DAX in short. And in addition to the conservative properties of this method, an important characteristic is that the time step is not restricted by the collision time, and relatively large CFL numbers can be used for the simulation. So our target is to reformulate the DAX algorithm within a framework of adaptive reference frames in space and time. The underlying kinetic model that is used consists of the two population models. The density and the momentum are conserved from the F populations, and the second population, the Gs, they are designed to carry the excess internal energy and to modulate the adiabatic exponent. Again, a brief short overview about the point. So the main idea is that to construct discrete velocities, we need to select a reference frame, and we define it using a reference velocity and the reference temperature. In traditional LB models, the reference frame is assumed to be constant across the simulation domain, zero velocity and scaled with the lattice temperature. In PONT, however, each point in space and time uses its own reference frame, which is characterized by the local flow velocity and temperature, and we term it as the co-moving reference frame. And the key advantage of this approach is that the equilibrium populations in the co-moving reference frame become exact and they do not depend on the velocity. For the actual implementation of PONT, the first task is to relate populations at different reference frames. And to accomplish this, we will use the one-to-one relation between the population and its vector of moments, also that the moments are independent of the reference frame. The second element that needs to be addressed for the realization of PONT is an iterative scheme, typically a predictor corrector loop that break the implicitness. And the reason for this implicitness is that the particle velocities depend on the local flow velocity, which is not known a priori. Now we will explain the basic steps of the DAX and the finite volume discretization, focusing for simplicity on the F populations. The same procedure that will be outlined here is also holds for the second population. The starting point of the analysis is the continuous BGK equation. We integrate spatially over a cell and a long time, using the midpoint rule for the convection term and the trapezoidal rule for the collision term. After the integration, we arrive at the following discrete equation, where now the F's are the cell average population, and the capital Fi's designate the population flux over the cell phases. And we notice that this equation is implicit due to the collision term on the right-hand side. To avoid the implicitness, we use the following variable transformation, which is also incorporated in the standard LB formulation. Substituting the new populations, we arrive at our final equation, which is used to update the populations in the cell. The alpha and beta coefficients depend on the time step and the relaxation time in a similar fashion as LBM. The main difficulty here in this equation is the calculation of the fluxes. So let's see how we evaluate them. Let's focus on this simplified diagram. The horizontal axis represents the space, with the solid cubes showing the cell centers. Time step n, we know the populations at the centers, and what we need in order to evaluate the fluxes are the populations at the faces of the cells, and time step n plus a half. And to compute these populations, we essentially apply a half time step LB step, and to perform this explicitly, we again use the variable transformation as shown by the populations with the overlap. The flux evaluation can be summarized in the following steps. So first, compute the transformed populations at the cell centers and the spatial gradients. And for high Mach flows with discontinuities, slope limiters such as the Van Leer limiter, they are used for the gradient computation. We then perform the pond streaming step. So the reference frame is initialized with the flow fields from the previous time step, and we calculate the departure point. Using the cell centers data and the spatial gradients, we can linearly reconstruct the populations at the departure point. And with the populations calculated, the flow fields at the cell faces are now evaluated, and the loop is repeated until the reference frame converges. And at the end of this step, we use the transformation to obtain the F populations and evaluate the fluxes. We should also note that at this point, if instead of the pond iterations, we use a constant reference frame and just a linear reconstruction of the departure point, we retrieve also the original DAX algorithm. So now we can show an overview of the pond DAX algorithm, identifying the following phases. At the beginning of the time step, we have the populations and the flow fields defined at the cell centers. With this input, we can calculate the transformed populations, the F bar, and the spatial gradients at each cell center. So the second phase consists of the flux evaluation at every cell phase. And this is the phase where the pond iterations take place. And at the final phase, we update the populations at each cell center using the fluxes from the previous phase and calculate the flow fields. We proceed now to the validation of the scheme, starting with a classical benchmark of the Lux Shock Cube. So the velocity set is the D2Q9, the adiabatic exponent set to 1.4, and the CFL number is set to 0.4. And with this imposed initial conditions, this case corresponds to an initial pressure ratio of 10 across the middle of the cube. And the figures below show the density, the velocity, and the pressure profiles superimposed with the analytical solution, the exact solution, and we can see that the results in general agree very well with the reference solutions, with a very, very small degree of oscillation. The next case is the Lux Shock Cube, which we simulate with the D2Q25 and with the same simulation parameters. The Mach number for this case is greater than the previous, and in general, it's a more challenging simulation of the Shock Cube. But again, we observe that the profiles match very well with the reference solutions, again, with only a very small degree of oscillation. The last 1D validation case is the Schwarzer Problem. In this problem, the shock wave of Mach 3 interacts with a perturbed density field, leading to discontinuities and small structures. The simulation is set with CFL number to 0.2, and the domain is discretized with 800 points. The left diagram shows the initial conditions for the density profile, while the right diagram shows the final results. And we can see that the shock locations are captured very well, and also that the small structures agree very well with the reference solution. The next problem to study is a 2D Riemann problem, which is also a benchmark test case for compressible solvers. The model consists of the D2Q9 set with a CFL number set to 0.3. The simulation is initialized by dividing the domain into 4 quadrants, each of which is set to constant values of flow fees, as shown in the configuration on the right. For boundary conditions, we apply 0 gradient at the populations at each boundary of the domain. And, what we expect to see from this setup are emanating shock waves from the interfaces, propagating towards the upper right corner, and the development of small structures due to the interaction of the waves near the middle. So here we can see the results for the density profile for 3 different resolutions. And also on the bottom row, we can see a zoom in towards the center of the domain of density contours. And in all cases, we see the propagation towards the right upper corner, as well as the development of finer structures with increasing resolution. And in general, these results match very well the corresponding results from the literature. The final case is a 2D high-Mach jet flow, which is being injected into the domain, which is initially full of gas at rest. At the inlet, we impose a Mach number of 50, and zero gradient boundary conditions are applied to the rest of the boundaries. The velocity set is the D2Q9 and CFL number to 0.2. And here in the two figures, you can see the results for the density and the pressure profiles, where we see the shock propagating into the medium. And also we can notice the large ratios between minimum and maximum pressure, more than 2 orders of magnitude. In conclusion, the particles on demand method was tested with a finite volume discretization, in particular the discrete unified gas kinetic scheme, which is a conservative formulation. The DAX, the POND DAX scheme was validated with a series of 1D and 2D problems, showing a very good agreement with the benchmarks. In general, using an adaptive reference frame formulation in DAX, it shows a considerable improvement of the operating range of the kinetic models, similar with what we have seen with other POND methods. And finally, more work will be pursued on the flux evaluation and the spatial reconstruction, further testing on more demanding cases and also 3D problems. Thank you very much.
Thank you. Thank you for your presentation. If there are questions, I think there is already one, the first. Okay. In the chat. Oh, oops.
So this method is second order, both in space and time. From what the viscosity.
Okay, question.
So the viscosity, you set the viscosity through the relaxation parameter.
Okay.
In general, no, it does not depend on the propagation method. And let me read the other one.
Okay, the second adaptive GKS have already been published in the past. How does your approach compare with this approach in terms of accuracy, robustness, and efficiency?
So this work here, what we show, so it's the implementation of the POND ideas into this finite volume method. So of course, the ideas of adaptive reference frame we know from the past, but the main attribute of POND is how you can formulate this idea into the LB setting. So through the iterations and through the moment matching. So in general, it's a quite fresh work. So we are now investigating into the range of the scheme, which up to now it has shown quite positive results, but we're still in an initial phase of development. So I could not now comment on the comparison, but we definitely have seen an improvement of, let's say, the original DAX compared to POND and DAX.
If I may, I have another question.
Yeah,
Please.
Could you come back on the slides where you showed the Lux Shock Cube with the D2Q9? Because I think that you forgot to say something here. You are using two populations, right?
So
the one before this one. Sorry.
Here, right?
You are using two populations, right?
Yes, yes.
Yeah, because if you use only one population, since you do not have the right third order moment, you will have a mismatch on the temperature field.
Sorry, everywhere we use the two population model.
Yeah, but that's the trick, in fact, because if you were using one population, since you have been saying for like 3 talks that with the Q9 formulation it works, it doesn't work. You do not have the right third order moment. And this can be easily shown, in fact.
But in the common reference frame, also the third moment is, so if you compute...
Did you compute the deviation with respect to the third order moment, and did you show that it is equal to machine precision, the error?
You can compute, yes, so the third moment and the fourth, so in the co-moving reference frame only, it is...
I mean, this is extremely weird because we implemented it and we have issues on the temperature field, and we showed that it's because of the third order moment. In fact, it's in the backup slides of my presentation of yesterday. This can be easily checked on ResearchGate. I just uploaded it.
So you can also check our paper. So we
in the paper you use two population. If you use two population, that means that you're dividing the resolution of mass and momentum equation from temperature. And for mass and momentum equation, you need up to second order moments for the convective fluxes. So Q9 works. But if you want further to do all the physics with Q9, then you need third order moments. And this doesn't work because you do not have enough moments with the Q9 formulation. You only have 9 moments because there is a direct bijection between the velocity space and the moment space.
So, but so you have a mistake in your thinking, because the whole concept of point, if you go on paper and
no, but this is basic mathematics. Huh? Did you compute by hand the third order moment in the co-moving reference frame, and did you show that you get the right one?
Yes. So you can also.
Yes. Which paper? Which
third
paper?
order moment.
I want to see the paper. Which
the multi-scale.
No, multi-scale. You have 2 populations. Don't lie.
No, but you can still see the equilibrium moment using the D229 only there. So
you are saying on record. Are you saying on record that using 1 population, 9 velocities, you do not have any issue with the third order moment?
So what I'm saying is that with the co-moving reference frame, so only when you have the co-moving reference frame, then the third order moment is the correct one. But only if you use the co-moving reference frame, and this is why
with 1 population.
Also or if you just compute with 1 population.
With 9 velocities.
I think we got the point about 1 or 2 populations.
Yeah, so with
at least
if you consider just 1 population, and if you compute the third,
it is clear the question and the answer. I don't want to how you say, give a penalty to the people that do question through the chat. There is a comment by Irina. She wrote also the UGKS scheme of XU is a fully Eulerian, while this formulation has an half step of Lagrangian streaming.
That's correct. And the DAX is in general a combination between unified gas kinetics and LBM. So it's a unison between these 2 methods. So this is why the half-time Lagrangian streaming enters the game in this formulation. That's
okay. Thank you. Okay, thanks again. And I think now we have a coffee break of 20 minutes. So we will see later at 11 and 20. Thank you very much. And have a good coffee break.